Probability in set theory. Essential question. How are sets and their relationships used to calculate probability? Well, to calculate the probability of an event, you need to know the number of items in the set of outcomes for that event, as well as the number of items in the set of all possible outcomes. The theoretical probability is a ratio of those two events. So working with sets. A set is a collection of distinct objects. Each object in a set is called an element of the set. A set is often denoted by writing the elements in braces. The set with no elements is the empty set, denoted by the null sign or empty brackets. The set of all elements under consideration is a universal set, denoted by U. Identifying the number of elements in a set is important for calculating probabilities. All right. A. Use set notation to identify each set described in the table and identify the number of elements in each set. So I'm going to need to make this a little bit smaller. Let's go with 125. Yeah, there we go. We can get that. All right, that's all in there. So set A is a set of prime numbers less than 10. So that would be 2, 3, 5, and 7. And if you'll notice, there's 4. 1, 2, 3, 4. 4. All right. Set B is a set of even natural numbers less than 10. 2, 4, 6, and 8. And there's 1, 2, 3. There's 4 of them as well. So the number in element B is, or set B, is 4. Set C is a set of natural numbers less than 10 that are multiples of 4. So set C is going to be 4 and 8, and the number in set C is 2. There are 2 of them. The universal set is a set of all natural numbers less than 10. And so we got a bracket here. So what do we got? What's less than 10? 1, 2, 3, 4, 5, 6, 7, 8, and 9. So that would be the universal set. And the number in the universal set is 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's 9 of them. All right. And let's see here. The following table identifies the terms used to describe relationships among sets. Use sets A, B, C, and U from the previous table. You will supply the missing Venn diagrams in the example column, including the reference elements of the sets as you complete steps B through I following. So let's see here. I'm going to, let's see, well, that all fits on there just like that. So I'm going to take a picture of that. All right, good. Now, let's see here. Let's go down and look at B. And let's jump that back up to 150. So, there we go. Since C is a subset of B, every element of set C, which consists of the numbers 4 and 8, because that's what's in set C, 4 and 8, is located not only in oval C, but also within the oval B. Set B includes the elements of set C as well as the additional elements 2 and 6, which are located in oval B outside of oval C. The universal set includes the elements of set B and C as well as the additional elements 1, 3, 5, 7, and 9, which are located in region U outside of ovals B and C. Okay, so let's draw that. And let's go back to the table here and let's draw that. So we have and so here it is. the universal set. And then we have a set, and we'll use this here. This is going, well, we'll call this B. Let's draw that right there. And inside of B will be C. All right. Now, what was in C? What was in element C? You had 4 and 8, right? 4 and 8. Now, what was in B? B had 2, 4, 6, and 8, right? All right. Now, what was in the universal set? 1, 2, which we already got, 3, 4, which we already got, 5, 6, which we already got, 7, 8, which we already got, and 9. Okay, so that covers all the numbers. This C is also a part of B, so that's why they're both highlighted. Okay, in the first row of the table, draw the corresponding Venn diagram. So C table. We just got through doing that. All right. Let's see here. Oh, yeah, we can get it all on there. To determine the intersection of A and B, first define the elements of set A and set B separately, then identify the elements found in both sets A and B. So in set A, there was 2, 3, 5, and 7. Those are the prime numbers less than 10. In set B, it was the even numbers less than 10, which is 2, 4, 6, and 8. 2, 4, 6, and 8. Now, what is common to both? Well, if you look, 2, are there any others? Nope, just 2. 2 is the only thing common to both. Okay. Now let's go back and draw that in the table. So let's see here. We got all right. So we're going to have A, and then what color did we use for A? We used blue, and then green for, so blue, we're going to use blue. Let's draw us an oval, and we'll use blue. And then we used green for other. All right. So what was in both? Well, and then let me, this covers this. All right. 2. 2 was in both, so it's shaded in both. And then what was in A was 2, and then it was 3, 5, and 7. And then in here it was 2, 4, 6, and 8. Now, what about in the universal set? 1, it's not included in either. 2, 3, 4, 5, 6, 7, 8, and 9. Okay, so 1 and 9 was left out. They're the only thing in the universal that was not in the others. Okay, good. And let's look at E. In the second row of the table, draw the Venn. So we'll just say C table. All right. To determine the unions of set A and B, identify all of the elements found in either set A or set B by combining all the elements of the two sets into the union set. Okay, so A union B. That's going to be 2, 3, 4, 5, 6, 7, and 8. Okay. To determine the union of sets A and B, identify all the elements found in either set A or set B. Okay, so that's combining them. Let's go back and draw that. So and then let's see here. Let's use this. Will probably be easier to see. And I didn't mean to drop that little one there. So 2, and then 3, 5, and 7, and 4, 6, and 8. And the only thing in the universal set that wasn't in here was 1 and 9. Okay. All right. So the entire shaded region. Good. We already did that. In the third row of the table, we did that. So C table. C table. All right. To determine the complement of set A, first identify the elements of set A and the universal set separately. Then identify the elements in the universal set that are not in set A. So set A was 2, 3, 5, and 7. The universal set is 1, 2, 3, 4, 5, 6, 7, 8, and 9. So the complement is going to be the elements that are in the universal set that are not in A. Okay, so what's in A? And let's see. So we don't want to use 2. We don't want to use 3. We don't want to use 5 or 7. So what do we have left? 1, 4, 6, 8, and 9. In the fourth row of the table, okay, so we'll say C table, and we'll go back and draw that. So let's go here, back, and we'll draw that in there. So let's see here. This time, and we'll do that in yellow. Covered that up. Ha. And then we need an oval that's not shaded. So let's grab this and we'll make it white. All right. And so what was in A? What was in A was 2, 3, 5, and 7. 2, 3, 5, and 7. And what's the complement? The complement is going to be 1, 4, 6, 8, and 9. Okay, those are the highlighted ones. Good. Going well. I don't know why I did that. All right. Reflect. Draw conclusions. Do sets always have an intersection that is not the empty set? Provide an example to support your conclusion. No. No. Using the examples above, A intersection C is the empty set. I don't know why I did that. Is the empty set. Okay, because they do not have any, because they do not have any elements in common. All right, good. A probability experiment is an activity involving chance. Each repetition of the experiment is called a trial, and each possible result of the trial is termed an outcome. A set of outcomes is known as an event, and the set of all possible outcomes is called the sample space. Probability measures how likely an event is to occur. An event that is impossible has a probability of 0, while an event that is certain has a probability of 1. All other events have a probability between 0 and 1. When all the outcomes of a probability experiment are equally likely, the theoretical probability of an event A in the sample space S is given by the probability of A equals the number of outcomes in the event divided by the number of outcomes in the sample space. All right. Calculate the probability of A, the probability of A union B, the probability of A intersection B, and the probability of A, or the complement of A, for each situation. You roll a number Q. Event A is rolling a prime number. Event B is rolling an even number. Okay. So the sample space is 1, 2, 3, 4, 5, and 6. That's each side of the die. Okay. A is the prime number. That would be 2, 3, and 5. And so event B would be 2, 4, and 6. All right, go ahead and read through A, and when you get back, we'll do B together. Your grocery basket contains one bag of each of the following items: oranges, apples, green apples, green grapes, green broccoli, white cauliflower, orange carrots, and green spinach. You are getting ready to transfer your items from your cart to the conveyor belt for checkout. Event A is picking a bag containing a vegetable first. Event B is picking a bag containing a green food first. All bags have an equal chance of being picked first. So let's see. Your sample space is orange, apple, grape, broccoli, cauliflower, carrot, and spinach. So S equals, let's see here. S equals 1, 2, 3, 4, 5, 6, 7. So the number is 7. Now, A, you have broccoli, cauliflower, carrot, and spinach. All right, so 1, 2, 3. So the number of A is 4, and the probability of A over S would be 4 over 7. A union B would be broccoli, cauliflower, carrot, spinach, apple, and grape. So A union B would be 6. Let's see, 1, 2, 3, 4, 5. Yeah, 6. So what do we got? The probability of A union B would be the number of A union B divided by the number of S. Well, there were 6 in this, and there were 7 in that, so your probability is 6 over 7. A intersection B would be broccoli, spinach. That's what's in both. So A intersection B, or the number of A intersection B, would be 2. So you have the number of A intersection B divided by the number in the sample space. That's going to be 2 over 7. How about the probability of A complement? So that's going to be the number of A complement divided by the number of S. And A complement, well, that's going to be 3 and 7. How did I get 3? Well, I looked and saw how many are in A. 4. So that means 3 aren't. Okay. All right, good. Reflect. In example 1B, which is greater, the probability of A intersect or A union B, or the probability of A intersection B? Do you think this result is true in general? Well, let's see. The probability of A union B was 6 over 7, right? And the probability of A intersection B was 2 over 7. Okay? So I would say this is going to be, and in most cases it will be. The union is more likely. The union is more likely than the intersection. And it's probably generally true since the union includes all elements. The union is more likely than the intersection because the union is the the union is the amount. I don't like it. The union is all elements of both. Wow. The intersection is units that are in both. Let's see. Do you think this result is true in general? Yes. The union is all elements of both, while the intersection is the units that are in both. Okay, so more than likely the union will be a higher probability than the intersection. And the only time that might not be the same, or the only time that would be the same, is if set A equaled set B. They were the same. All right. Let's see. The numbers 1 through 30 are written on slips of paper that are placed in a hat. Students draw a slip to determine the order in which they give an oral report. Event A is being one of the first 10 students to give the report. Event B is picking a multiple of 6. So let's see here. A is being one of the first 10 students, so that's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. And in event B, so B is picking a multiple of 6. So what do we got? We got 6, 12, 18, 24, and 30. All right. If you pick first, calculate each of the indicated probabilities. Probability of A. So the probability of A would be the number of A divided by the number of the sample space. Well, how many is in A? 1, 2, 3, 4, 5, 6, 7, 8, 9. That's 10, and there's a total of 30, so that's going to be 1/3. All right, the probability of A union B, okay, so that's going to be the number of A union B divided by the number of the sample space. So we know 30 is in the sample space. So what do we got? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But we don't count that one. 11, 12, 13, 14. So we get 14 over 30, which is 7/15, right? The probability of A intersection B would be the number of A intersection B, what's in both, and the number of S. So what's in both? What's in both? Well, you got a 6 here and a 6 there, so that's going to be 1 over 30, right? All right, good. And then the A complement. So that's going to be the number of A complement over the number of S. So how many is in A? 10. Well, 30 minus 10 is 20, so that's going to give you 20 over 30, which is 2/3. Not bad, not bad. All right, using the complement of an event. You may have noticed in the previous example that the probability of an event occurring and the probability of an event not occurring, i.e., the probability of the complement of the event, have a sum of 1. This relationship can be useful when it is more convenient to calculate the probability of the complement of an event than it is to calculate the probability of the event. So the probability of A plus the probability of the complement of A equals 1. Probability of A equals 1 minus the probability of the complement of A, and the probability of the complement of A equals 1 minus the probability of A. All right. Example 2. Use the complement to calculate the indicated probabilities. And I'll let you read through A, and when you get back, we'll do B together. One pile of cards contains the numbers 2 through 6 in red hearts. A second pile of cards contains the numbers 4 through 8 in black spades. Each pile of cards has been randomly shuffled. If one card from each pile is chosen at a time, what is the probability that the sum will be less than 12? All right, define the event. Let A be the event that the sum is less than 12, and A complement be the event that the sum is not less than 12. Make a diagram, complete the table. Well, let's see, 4 and 2, that's 4 and 3. 4 and 4 would give you 8. 4 and 5 would give you 9. 4 and 6 would give you 10. 5 and 2, 7. 5 and 3 is 8. 5 and 4 is 9. 10 and 11. And then 6 and 2 is 8. 9, 10, 11, and 12. 7 and 2 is 9. That would be 10, 11, 12, 13. That's 10, 11, 12, 13, and 14. All right, circle the outcomes in the table that correspond to the complement of A. And let's see, the sum is not less than 12. So that's going to be all of these here. Okay, so we got 1, 2, 3, 4, 5, 6. So that's going to be 6 right here. That's going to be the number of the complement of A divided by the number and the sample, which is 1, 2, 3, 4, 5. 1, 2, 3, 4, 25. Okay, that's not difficult at all. Step 4, determine the probability of A. Use the relationship between the probability of an event and its complement to determine A. So we have the probability of A is 1 minus the probability of the complement of A, which is 1 minus 6 over 25, which is 19 over 25. So the probability, the sum of the two cards is less than 12 is 19 over 25. Use a different way to calculate the probability that the sum of the two cards will be less than A. Well, you can use the table to count the number of outcomes in event A instead of the complement of A, which is 19. Then divide that by the total number of outcomes to get 19. So basically, you're just going to go over here and we'll use blue. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So that gives you 19, and then there was 25 total, so 19 over 25. All right. Your turn. A bag of marbles contains 2 red, 1 yellow, and 1 green. 2 red, 1 yellow, 1 green, and 1 blue marble. So I'm going to draw a bag here. I like to draw a bag. And let's see here. Let's draw a bag. Okay. So we got this bag here, and we have 2 red, 2 red. We have 1 yellow, 1 yellow. That's kind of hard to see, isn't it? And let's see, 1 green, 1 green, and 1 blue marble. Okay. And then another bag. So let's draw us another bag here. Draw us another bag. And 1 marble from each bag. Okay. And another bag contains 1 marble of the same 4 colors. So we've got a red, a yellow, a green, and a blue. All right. Now, use the complement to calculate the indicated probabilities. Okay, let's do that. Probability of selecting 2 different colors. Well, so the complement will be selecting the same color. Let's see, the complement would be selecting the same color. All right, so if we were to say that would be there's 2 reds in here, so you got red 1 and then red, right? And then you have red 2, and then a red. And then you have a yellow and a yellow, and a green and a green, And then, of course, a blue and a blue. Okay. So the probability of A complement would be 1, 2, 3, 4, 5. That's 5 over 20, which is 1/4, right? Well, how did you get 20, Mr. Carbonell? You got 1, 2, 3, 4, 5 in here, and you got 4 in there. 5 times 4 equals 20. Okay. So the probability of A would be 1 minus the probability of A complement, which is 1 minus 1/4, or 3/4. Okay, there's your answer, 3/4. All right. Probability of not selecting a yellow marble. Okay. Well, so the A complement will be selecting a yellow marble. Okay, so what do we got here? Well, let's see here. You have, if you draw from this bag here first, you got yellow, red, and yellow, 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 green, yellow, blue. All right. So that's if you draw the yellows first. And then you have, if you draw a red one, let's see here, red 1, yellow, red 2, yellow. Now, you've already drawn yellow, yellow, so you don't include that again. And then you have green, yellow, and you have blue, yellow, right? Okay, so how many is that? 1, 2, 3, 4, 5, 6, 7, 8. So the probability of A complement is 8 over 20, which is 4/10, 2/5. 2/5. Okay, 2/5. So the probability of A would be 1 minus the probability of A complement. 1 minus 2/5 is 3/5. And believe it or not, on that one there, number 9, it was actually easier to calculate the complement than the real, because I think you would have had to do all them other ones. So that's one they sometimes use the complement, because they say it's cheaper. Can a subset of A contain elements of the complement of A? Why? Well, no, it can't. Why? Well, because by definition, the elements of the elements of a subset are contained completely within the parent set A, whereas none of the elements of the complement of a set A are in the set A by definition, and thus they cannot be in a subset of A. So, can a subset of A contain elements of no? Uh, by definition, by definition, uh, they would not. They would not contain the same elements. All right. For any set A, what does A intersection the null set equal? What does A union the null? So A intersection, the empty set, is the empty set. Okay? Since the two sets do not have any elements in common. Remember, this right here is empty bracket. There's nothing in it. That's the null set. So is equal to the null set because they do not have any, because they do not have any elements in common. What about A intersection empty set? Well, what is that going to equal? It's going to equal A. Why? Because you combine all the elements of both sets. And since the empty set has no elements, it's just what's in set A. Essential question check-in. How did the terms set, element, and universal set correlate to the terms used to calculate theoretical probability? Well, remember at the beginning I said to calculate probability, you need to know the number of possible outcomes in the sample space. Okay, let's see here. To calculate probability, you need to know the number of possible outcomes in the sample space which happens to also be called the universal set in set theory. You also need to know the number of possible outcomes in the defined set. Okay, this right here is the denominator. It is the sample space. It is all. This right here is the numerator. It is the defined set, like A, or probability of A, or the probability of the complement of A, or whatnot, which is the number of elements in the defined set. And remember, probability is the ratio of the two. All right, great lesson, folks. I hope you have a wonderful evening, and I'll see you tomorrow in class.